In Proton NMR, a signal does not always appear as one simple peak. Sometimes it splits into 2, 3, or 4 lines. Today, we will learn why this happens using the n+1 rule. Proton NMR gives 4 main signals. The number of signals tells us how many hydrogen environments there are. Chemical shift tells us the type of environment. Integration tells us the relative number of hydrogens. Splitting tells us how many neighboring hydrogens are next door. Splitting is a neighborhood signal. A signal is split by neighboring protons, usually hydrogens on the adjacent carbon. This is a common mistake. The 3 hydrogens in CH3 do not split their own signal, meaning same environment equal no splitting. Splitting comes from neighboring hydrogens, not from hydrogens in the same environment. For simple A-level proton NMR questions, we use the n+1 rule. If there are n equivalent neighboring hydrogens, the signal is split into n+1 lines. The n+1 rule tells us the number of lines. Pascal's triangle tells us their relative heights. A triplet has a 1:2:1 pattern. A quartet has a 1:3:3:1 pattern. Let's begin with bromoethane, CH₃CH₂Br. There are 2 proton environments, the CH3 group and the CH₂Br group. The CH3 signal is split by the 2 hydrogens on the neighboring CH2. So n is equals to 2. And since number of lines equals to n+1, hence n+1 is equals to 3. So CH3 gives a triplet. The CH₂Br signal is split by 3 hydrogens on the neighboring CH3. So n is equals to 3. Hence, number of lines is equals to n+1. Hence, we have 4 lines. So CH₂Br gives a quartet. Now we check the spectrum. The signal near 1.23 ppm is the CH3 triplet because there are 2 neighboring hydrogens. So 2 + 1 equals to 3, hence triplet. The signal near the 3.29 ppm is the CH₂Br quartet because CH2 is linked to 3 neighboring hydrogens. So 3 + 1 equals to 4, hence a quartet. The CH₂Br signal is further downfield because bromine is electronegative. Integration and splitting are different. Integration tells us how many hydrogens cause the signal. Splitting tells us how many neighboring hydrogens are next door. For our CH3 signal in CH₃CH₂Br, the integration equals to 3 hydrogens because we have 3 hydrogens in the same chemical environment. The neighboring hydrogen equals to 2 because there are 2 neighboring hydrogens. Therefore, using the n+1 rule, splitting or the number of lines observed will be equals to 2 + 1 equals to 3 or triplet. Now, let's look at butanone, CH₃COCH₂CH₃. There are 3 proton environments: CH3CO, CH2, and the terminal CH3. For CH3CO, the adjacent carbon is the carbonyl carbon, which has no hydrogen atoms. So, N equals to 0. Using the n+1 rule, we will have 0 plus 1 equals to 1, hence a singlet. The CH2 group is next to CH3, so the neighboring hydrogen atoms equals to 3. Using the n+1 rule, n+1 is equals to 3 plus 1 equals to 4. Hence, it gives a quartet. The terminal CH3 is next to CH2. So, n equals to 2. The number of lines observed will follow n+1 equals to 2 plus 1 equals to 3. Hence, it gives a triplet. Now, we check the butanone spectrum. The terminal CH3 appears as a triplet because it has 2 neighboring hydrogens. So, 2 plus 1 equals to 3. Hence, a triplet. The CH2 appears as a quartet because there are 3 neighboring hydrogen atoms. So, applying the n+1 rule, 3 plus 1 equals to 4. Hence, CH2 appears as a quartet. The CH₃CO signal appears as a singlet because the adjacent carbonyl carbon has no hydrogens. So 0 plus 1 equals to 1, hence a singlet. This is why butanone is a useful trap. Not every CH3 group gives a triplet. The CH₃CO group gives a singlet because the adjacent carbonyl carbon has no hydrogens. Now, let's look at these two examples. This carbon is connected to 2 neighboring hydrogen atoms. So, it will display 3 lines. Because 2 plus 1 equals to 3, it will give a triplet. But, if you look at the example over here at the bottom, this carbon is connected to a carbonyl carbon which has no hydrogen atoms. Therefore, it will display a singlet because 0 plus 1 equals to 1. Hence, not every CH3 gives a triplet. This gives a triplet. This gives a singlet. Therefore, it is important to always check the adjacent carbons. The biggest mistakes are counting hydrogens in the same group and forgetting the adjacent carbon and mixing up integration with splitting. For simple questions, count equivalent hydrogens on the adjacent carbon. So, same group, do not count. Adjacent carbon, count. Quick check. In CH₃CH₂Br, what splitting pattern does the CH3 signal give? The CH3 group is next to CH2. So, N is equals to 2 because there are 2 neighboring hydrogen atoms. So, N plus 1 equals to 2 plus 1 equals to 3. So, the answer is triplet. To summarize, the number of signals tells us the different hydrogen environments. Chemical shift tells us the type of environment. Integration tells us the relative number of hydrogens. Splitting tells us the neighboring hydrogens. So remember, splitting pattern equals to neighborhood clue. In the next video, we will look at integration, how the area under each signal tells us the ratio of hydrogens in different environments. If you want to learn more about A-level chemistry, be sure to subscribe to this channel, and I'll see you in the next one.